Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy here at Foothill College in Los Altos Hills. And it's a great pleasure for me to welcome everyone here in the Smithwick Theater and everyone watching or listening to us on the web to this, the 26th year of the Silicon Valley Astronomy Lecture Series. For the last 26 years, we brought 6 lectures a year to the public at no charge, and we've also been able to, for many of those years, to bring the lectures via YouTube and now via podcast to a much wider audience. We're being watched and listened to all over the world, and I want to welcome all of you wherever you are listening to us. These lectures are sponsored by 3 organizations: the Foothill College Science, Technology, Engineering, and Math Division, the SETI, or Search for Extraterrestrial Intelligence Institute, which is headquartered here in Mountain View, and the Astronomical Society of the Pacific, a 136-year-old organization which does what we try to do in these lectures, to essentially help the public understand astronomy. And we're very grateful for all these organizations for their help. Tonight, to start things off with a bang, we thought it would be really exciting to talk about what is, if I may say, the sexiest project in astronomy going, the Vera Rubin Observatory, which is going to take the most amazing movie of the sky. I don't want to steal the speaker's thunder. And we're honored to have with us the Dean of Science at Berkeley, Professor Stephen Kahn, to talk about this observatory. Before I introduce him, let me just say, those of you who are not regular viewers or listeners, if you're on YouTube, we ask you please to click the bell and subscribe, and that way you'll be notified of lectures to come and when the lectures get put up on YouTube. And okay, now without further ado, let me introduce Professor Kahn. He is the Dean of Mathematical and Physical Sciences and a professor of physics and astronomy at the University of California, Berkeley. He is the former director of the Vera C. Rubin Observatory, so he's the perfect person to tell us about the plans for this very exciting instrument. He was a professor of natural sciences at Stanford and also a professor of physics and astronomy at Columbia, the 2 schools where he got his degrees. He's an experimental astrophysicist and cosmologist who has made major contributions in science to multiple fields. He was the U.S. principal investigator on a spectrometer experiment launched with the European XMM Newton Observatory in 1999. More recently, he served as the director of the Rubin Observatory construction project from its beginnings in 2013 until his move to Berkeley in 2022. Professor Kahn is an elected fellow of the American Academy of Arts and Sciences and an elected member of the National Academy of Sciences. So we are honored to have him here to describe to you the survey of the universe to be performed by the Vera C. Rubin Observatory. Professor Kahn.
Thank you very much, Andy, for this invitation. It's a pleasure to come out here. I was at Stanford for many years, so I lived in the area, so I'm well familiar with Foothill College and with Los Altos, et cetera. It's wonderful to come back. And thanks to all of you for coming out on a Wednesday night. I know that's not easy, but this is a great community, one that's always interested in intellectual topics, and it's wonderful to see the public come for such events. So I'm going to tell you about the Vera Rubin Observatory, which you may have seen some things about in the newspaper. It's after many, many years of construction, it sort of came online this year. And we released the first images in June at a major press conference that was held in Washington. We've been commissioning the observatory since we took first light in April. And we're about to start the 10-year survey of the southern sky, which I'll tell you about today. So it's an exciting time. It's very timely. I'm obviously biased, but I believe this facility is going to revolutionize a whole wealth of different fields in astronomy and in basic physics. Now, it's a big project, and like most large organizations, we have a mission statement. This is our mission statement. Rubin Observatory's mission is to build a well-understood system that will produce an unprecedented astronomical data set for studies of the deep and dynamic universe and make the data widely accessible to a diverse community of scientists and engage the public to explore the universe with us. So you'll note in transcribing the mission statement, I've put several words in bold, and I want to emphasize them. First, well understood. One way of thinking about the Rubin Observatory is that it's a statistics machine. For everything we know about today in the universe, the Rubin Observatory will produce a sample that's 10 to 100 times bigger than we already have. Now, as you know, if you have many, many more objects or many, many more samples, you can measure things more precisely. And a lot of the science that we're aiming to do with this observatory relies on that statistical power. But the statistical power is only as good as how well you understand your instrument. And in astronomy, over many decades and even centuries of experience, precision was not always the driving goal, okay? Mostly it was like, let's discover stuff, and we measure things to within a factor of 2, that's fine. That doesn't work for Rubin. So we will get well below 1% precision on many quantities of interest. And in order to have confidence in that result, you have to know exactly how your observatory works. And so from the start, we designed this mission to precisely define the requirements on every component of the system, and then to verify those requirements on the as-built article, and as we assembled all the pieces, to ensure that we understand in really intricate detail exactly how this observatory works. That not only includes the hardware we built, it also includes the atmosphere, because looking from the ground, we're looking through the atmosphere, so we put a lot of time into trying to understand in detail how the atmosphere affects our images. And that's a key element of the program. The next words in bolds are unprecedented astronomical data set. The data set acquired by the Rubin Observatory will be larger than the sum total of all astronomical images ever taken in human history. The total data set will be about 100 petabytes, which is 10 to the 17 bytes. At the time we started this project, we thought it would be the largest data set in the world. So this was very much a big data program. Now, it turns out it's not the largest data set in the world. Of course, big data has been a big thing, and now we're sort of in the running, but not near the top. But the analogy I find most useful is that our sum total of images will be a few percent of all the cell phone pictures taken by all the people in the world. A few percent, okay. It's not all of them, but even a few percent of all those pictures is something. And of course, we're saving all our pictures. And we will analyze all our pictures. So that gives you some idea of the volume and how much content is really there. And then the last set of words is accessible to a diverse and public community. So this is a public project. It was funded mostly by the National Science Foundation and the Department of Energy. And from the start, we designed and built it to make it available to everybody in the United States, everybody in Chile, which is where the telescope is housed, and many other people around the world that have entered into agreements with us from their various nations of contributions to the observatory. But it's not only for scientists. Rubin will be a discovery machine. And we put a lot of money into the data system. I'll talk a bit about that, but also into the public outreach system. So there are portals that exist that enable any interested person to log on your computer, access the data, fool around with it. The science that will come out of this project is essentially infinite. So it's not hard to think of something that nobody else has done. And we're hopeful that lots of people will just discover stuff for the first time using this data set in a way that's not been possible for a lot of other previous astronomical projects. So it's really to bring science home to everybody that's interested. And it's fitting to give this talk at Foothill College, so it's an example. Colleges like Foothill College and other community colleges in California and around the world can make use of these data as part of their teaching mission. I'll say later, we'll get something like 20 billion galaxies. We can give a galaxy to more than one galaxy to every person in the world. And they can study that galaxy and see, did anything happen? Did a supernova go off? And 250,000 times a year, a supernova will have gone off. And so if it went off in your galaxy, that's a pretty exciting event. You look at the data that day and like, oh my God, there's a new star there. So the intent here is to sort of bring home science to people, and that's what we're after. Okay, so this project was very broad-based, but there were a pretty quantitative set of science requirements that drove the idea. The idea behind this goes back to the mid-90s, and it started to take shape around 2000 or so to get the agencies interested. We had to figure out how to build it, which was not easy for reasons that I'll go through. We had to figure out where to put it. We chose a blank mountaintop in Chile. We're going to produce enormous amounts of data, so we needed a data center to store the data and to analyze the data. That turns out to be a few miles up the road at SLAC National Accelerator Laboratory, right here. We built the camera at SLAC, and the data from this mission will all be piped there and will be stored there and processed there. And it turns out that the design requirements on almost every element of this project, the telescope itself, the camera, the data system, we were pushing the state of the art in many different respects. So it was a challenging project to build. As a physicist, that's what made it fun. I put together a large team at SLAC, and we had another team in Arizona and lots of people distributed around the world that helped on it. Unlike many other projects, we decided not to build this project at one institution and require everybody who worked on it to come to that institution. We wanted the best people in the world to work on it, so we said, you can work on it wherever you live, and we'll organize the project that way. And we developed a remarkably distributed team that functioned very well. So the telescope is located in Chile on a mountain called Cerro Pachón, which is about 100 kilometers from the coastal city of La Serena. It's a well-developed astronomical area. It's one of the best sites in the world. It's about an hour's flight from Santiago if you're ever in Chile and want to visit up in that area. Okay, the project has gone by various names, and so people may have followed it during the course of its career, so let me just demystify some of that. It was originally called LSST, which for historical reasons stood for Large Synoptic Survey Telescope. Many people didn't know what the word synoptic meant. In fact, the person who invented that term, that title, didn't really know what it meant, turns out. He thought it meant something else. But it was applicable anyway. We went under that. We knew all along that's not a great a great name for a major facility, so it was renamed the Vera Rubin Observatory. I'll make a comment about that in a minute. We got a major gift, private gift, that got us started on this project from Charles Simonyi and also his friend Bill Gates. The two of them together gave us an initial starting amount of about $30 million, which was very crucial in getting it developed. That's Charles over on the right, and he named it after his father, who's shown next to him. So we actually call the telescope itself the Simonyi Survey Telescope. And then the camera, most of the telescope was funded by NSF. The camera was actually funded by the Department of Energy. That's why it was done at SLAC. And that is called LSST-CAM, because once you name something in the DOE world, it's essentially impossible to ever change the name. So it's the same acronym. And then because LSST was sort of well known in the community, we kept the acronym. We just changed what it meant. So we now refer to the 10-year survey that we'll do with this project as the Legacy Survey of Space and Time. And that's what LSST means now, but the name is still apt. But the acronym is still apt. Okay, this is a public-private partnership led by NSF. It's far and away the most complicated project that I or anybody else ever been involved with, because it's multi-agency, international cooperation, public-private. So all the ways that you can have conflicting entities that kind of get in each other's ways and make it hard to organize and administer. The NSF contribution was done as what's called a Major Research Equipment Facility Construction Project, MRFC. It was spec'd at $473 million. It started formally in August of 2014. Because of COVID, it ran over in time, and so we got an extra $85 million on top of that. The Department of Energy funded the camera as a Major Item of Equipment project, MIE, and that was $175.3 million, and we got an additional $47.9 million for commissioning. And the camera MIE was finished actually in 2021 for technical reasons, even though it was not on the telescope at that stage. And then, as I mentioned, we got this very important private funding of mostly from Simonyi and Gates, with a few other smaller contributors. That was about $34 million, and that was crucial. It was crucial because in order to get a project funded by the federal agency, a project of this magnitude funded by the federal agencies at this point, you need to prove that it's totally clear that you can build it for that amount of money. In order to prove that you can build it for that amount of money, you have to demonstrate that you've already sort of built it. Or they've already built the hard thing so that you know you can do the scale up. But you don't have any money before it's approved. So it's a real catch-22. And having private money is enough to get started so you can prove the feasibility and then eventually get the formal project. So this is going to be the new normal, I think, in big science projects. They're going to have to be public-private partnerships, because otherwise it's very hard to get around that mixed requirement. Okay, so what is the Rubin Observatory and why is it? Let me wait a minute. Yeah. So the Rubin Observatory is really about surveying the universe. And over the past couple of decades, there's been kind of a sea change in astronomy in the way we do it. Initially, over many years, astronomy was about selecting interesting stars or galaxies to look at, pointing a telescope at those objects one by one, taking images or taking spectra and measuring them. And a lot of the art of astronomy came from figuring out what stars and galaxies to look at, what was most interesting, and how are you going to derive conclusions from that. But about 20 years ago, it was recognized that you can only go so far with that. The universe is a big place. There's lots of objects. And there's tremendous value in just collecting enormous samples of things. And that's hard to do in a sort of what we call point-and-shoot mode. You know, if every observer has to propose to look at this particular star, you're not going to get through very many stars that way. So the aim was different. Let's build collectively, as a community, a survey of the sky and make those data generally available. The idea behind this really began with the Sloan Digital Sky Survey, which was a pioneering project in the early 2000s. It will culminate in the Vera Rubin Observatory. You could show, and I won't go through it here, that there isn't really a point in building another Rubin Observatory. We will already go deep enough to detect all the galaxies and stars in the universe that you can see before they start to blend into each other. And so there isn't much point in building something bigger or doing more of it. We're only looking at the southern hemisphere because that's all you can see from Chile. I frequently get asked, why don't you build a copy in the northern hemisphere? And the answer is, when you go faint, there's no difference between the southern hemisphere and the northern hemisphere. It's just a factor of square root of 2 in statistics. So this is really an end project. And that's one of the reasons I was personally attracted to it, is that it is the definitive project for this area of science. The data acquired by the Rubin Observatory are likely to transform nearly all fields of astronomy. As you'll see, it will dramatically affect our understanding of the solar system through mapping the orbits of millions of small bodies like asteroids, comets, et cetera. We'll measure all the varying stars in the sky, including explosive events and normal variable stars. We'll map out in excruciating detail the structure of the Milky Way galaxy, which will tell us how our galaxy was formed. And one of the most interesting things is we will study the structure and evolution of the universe in quantitative detail, sufficient to really get to some of the biggest mysteries currently facing physics, which involve the nature of dark matter and dark energy. So all those topics will come from the same data set. A colleague of mine who was a pioneer in this project, Tony Tyson, dubbed this massively parallel astrophysics. Take one large survey and do all sorts of different science from that same data set. Now, it's named after Vera Rubin. Her full name is Vera Florence Cooper Rubin. Rubin is actually her married name. We had the idea of naming it after her actually before she died. So we knew that there would be a new name, and we talked about who would we name it after, and Vera Rubin was a candidate. Unfortunately, she died in 2016 before we were able to accomplish that, and so it was done posthumously. Many of you may know who Vera Rubin is. She was a pioneering female astronomer whose work provided some of the most convincing evidence for the existence of dark matter, which is one of the great mysteries of modern astronomy and modern physics. Dark matter is the dominant form of matter in the universe, but it's fundamentally distinct from all the matter we're familiar with here on Earth. There's about 5 times as much dark matter in the universe as there is ordinary matter, which is the stuff we're made out of. Dark matter doesn't interact with ordinary matter, except through gravitation. So we believe there are dark matter particles floating through this room, floating through your body. You don't know they're there because they don't interact with any atom in your body. They just go right through you. The only way they interact with ordinary matter is through gravitation, but gravitation is a very weak force. So the gravitational effect of the dark matter in this room is essentially negligible. There's no way to know about it. But astronomically, there are concentrations of dark matter that we can detect because they have a gravitational influence on the matter that we can see. Vera's work was well recognized during her lifetime. She never received the Nobel Prize, which many of us believe she richly deserved. But we're proud to say that the Vera Rubin Observatory is the first major national scientific facility named after a woman scientist. And so we're very proud to carry that name and to recognize a true pioneer for the field and an icon that we hope motivates many young women to pursue science in general and astronomy in particular as they go forward. So what is the Rubin Observatory? The idea is very simple. You build a telescope that can take large format digital images of the sky very quickly so that the entire southern hemisphere of the sky can be observed in just a few nights. And then you do that over and over again for 10 years. We get something like between 800 and 1,000 images of every part of the southern sky. It's a pretty simple concept, but the implications are profound. So we'll measure, by comparing those different images taken at different times, we'll measure everything that moves in the sky. So things like asteroids, comets, stars themselves move due to the motion of the Earth around the sun. We call that stellar parallax. It's very important because it gives us a distance to stars. Proper motion, stars themselves are moving through space. We can measure that effect. We'll also measure everything that varies in time in the sky by looking at these different images. So stellar variation, stars themselves pulsate. There are binary stars which move around one another that causes variations. And then there are many forms of stellar explosions, really amazing stellar explosions that in some cases are there for about a month and disappear. In other cases are there for a few seconds or even a few milliseconds and then disappear. The universe is really a dynamic place. And these, of course, are very exotic systems. They typically involve black holes and neutron stars. And so they're very fun to study those kinds of objects. And including active galactic nuclei, which are massive black holes with masses like 1 billion times the mass of our sun at the centers of galaxies that power a lot of the exotic phenomena in the universe. So we measure everything that moves and we measure everything that varies. And then if you take these 1,000 exposures and add them all together, we basically measure everything in the sky. So we will get a sample of 20 billion galaxies and 17 billion stars. It'll be the first time in history that we know of more things in the universe than there are people on Earth. As I mentioned earlier, we can give everybody a few galaxies. You can have them. You can also have some stars if you want. And you can follow it and you can look at that. 20 billion galaxies is an interesting number because it's somewhere between 10 and 20% of all the galaxies in the universe. The universe is finite to us. The observable universe is finite. Why is that? Because light travels at a constant speed. So if you're looking further out in space, you're looking further back in time. And eventually, you go out far enough that you're looking at the beginning of the universe. So our universe, our observable universe, the real universe may be infinite, but our observable universe is 13.9 billion light years because the universe is 13.9 billion years old. And if you say how many galaxies are in a volume that large, it's somewhere between 100 billion and 200 billion galaxies. So we will be cataloging 10 to 20% of all the galaxies there are to catalog. That's a phenomenal thing. I mean, this is a human achievement that, you know, to some degree you want to do it just because you can. Just like, you know, in the early days when explorers discovered the New World, you wanted to map the New World because we can. We know something's there. Let's record it. And we can continue to look at those data for ages to come. Okay, so what's so unique about this observatory that it can do that? And the feature is something called the Etendue. The Etendue, it's a French word, an optics term. It refers to the product of the collecting area of the telescope, the size of the primary mirror, times the field of view of the camera. So it has units of meters squared, degrees squared. The field of view is an angular thing, so it's square degrees, and meters squared is the area of the camera. And that Etendue figure is basically an indication of how quickly can you survey the sky. And so one of the ways to think about that is, suppose you have a smaller mirror but a big field of view. With a big field of view, you can get a lot of the sky in every image, but with a smaller mirror, it takes you longer to get that image. Okay? Or equivalently, you can have a large mirror and a smaller field of view. A large mirror will take a shorter time to get the image, but you're only taking a smaller piece of the sky on every image, so you need more of them to cover it. So it's clear that it's the product that go together that makes the difference. Now, the Rubin Observatory mirror is actually not anywhere near the biggest mirror and telescope that exists today. In fact, there's another telescope called the Gemini South Telescope, which is on the same mountain. And on the left here, I've shown schematically the two primary mirrors of the facilities. For reasons I'll go into later, the Rubin Observatory mirror is actually an annulus, looks like a donut. It's about the same size as not in area, but in physical size, as the Gemini mirror. But on the right, again on the same scale, the smaller dot at the top is proportional to the largest field of view of any camera used in Gemini, whereas the big blue circle is the size of the field of view of the camera on Rubin. And remember, the Etendue is the product of those two. So you can see that the power for surveying the sky is much larger with Rubin. In fact, the Etendue is more than a factor of 10 of anything that exists today and anything that's even planned to exist by any agency or country on Earth. Nobody is planning on building anything that even comes within a factor of 2 of the Rubin Etendue. So it's really a world-unique project in terms of this particular function of surveying the sky. Now, just to give you an idea of the power of this, we spent a lot of time this is a simulated image. I'll show you a real image later. But this is a simulated image that we made. We had a very sophisticated program of simulation images that really tried to capture all of the engineering elements of the observatory, the atmosphere, et cetera. This image that I'm showing you is 1/200th of the full Rubin Observatory field. And it simulates what a picture will look like in a 15-second exposure with Rubin. So imagine something that's 200 times bigger than that picture. That's one 15-second snapshot. Okay, and we'll have something like 5 million pictures like that. But you can see the detail. Most of what you're seeing in this picture, this is just a blank region of space. Most of what you're seeing are galaxies. We go deep enough that you basically run out of stars. And as you look fainter, everything you're seeing are distant galaxies. The nearby galaxies are easily resolved. You can see them in the picture, but a lot of those faint little smudges, those are all galaxies. Okay, and it's all that total together that makes up this 20 billion galaxy sample that we'll have. Okay, that seems to have changed by itself. How did that happen? Wait a minute. Okay, sorry. Okay, so this slide gives you an idea of what happens when you go deeper. So believe it or not, these two images, these are both real images. And they're real images of the same field. On the left is an image from the Sloan Digital Sky Survey, which I told you was the previous survey facility. On the right is an image. It wasn't taken with Rubin, it was taken with another telescope, but at Rubin depth. But of exactly the same field on the same scale. So you can see that sort of bright central galaxy in the Sloan image. That's the bright galaxy you see in the center of the right. But look what happens when you go deeper. It just completely fills up with all sorts of things that were below the detection level before. So that's why the sample size is growing by huge factors. We're crossing a threshold where we detect all these things that simply weren't visible before. And you can see that those data are extremely rich. So, as I said, the idea is pretty simple. Why hadn't this been done before? Why is it hard? And these were challenges that we started. When we started this project in 2003, we needed to find a really good site, one that had good seeing, which means that the atmosphere didn't blur the images very much. And we needed a high percentage of cloud-free nights, and in particular that those cloud-free nights were evenly distributed over the course of the year. So we could observe everything in the sky without being too frequently affected by the weather. We needed to invent a new kind of optical system that could deliver large collecting area with a very large field of view. Our field of view is 10 square degrees, roughly. It's 40 times the size of the full moon. So if you look up at the sky on a night of a full moon, you see the moon, draw a circle that's 40 times bigger in area, that's one picture with Rubin. But because when you make big mirrors, big telescopes, if you try to go to a larger field of view, you get a lot of aberrations and things like that. You have to correct for all that. So this was not an easy challenge. Then we take pictures every 15 seconds, and then we go on to the next field, which is a few degrees away. So we're constantly moving this telescope around. Now, most big telescopes, you can't move around that fast, because when you move it, it kind of wobbles, and you have to wait for it to settle in order to be stable enough to take the next image or the next spectrum. We couldn't do that. We're moving around every 10, 15 seconds, 20 seconds, 30 seconds. So we needed a really stiff telescope design, and that was difficult. That hadn't really been done before. And so we wanted to keep what we call the slew and settle. How fast does it take you to move and steady, be ready for the next image? We wanted to keep that within 5 seconds. We needed to figure out what turned out to be the largest digital camera ever built. This is what we built at SLAC, just up the road. It's 3.2 billion pixels. One image, to display one image in its full detail, would take 1,500 of the highest resolution high-definition TVs just to look at the image. So that gives you kind of an idea of how many pixels are in this camera. And then we needed to figure out how to process, archive, and store enormous amounts of data. I mentioned this before. The data set is about 100 petabytes. At the time we started, there were no database tools that could handle this. The catalogs from Rubin will be trillions of lines long. And we need to query those catalogs fast and efficiently and in complex ways. So we had to invent a lot of new data reduction algorithms to enable that to work. Now, I mentioned if you're going to build a $1 billion facility and get the government to pay for it, you know, it's going to have requirements, and you're going to have a detailed cost and schedule. And you can't do that without starting with a set of concrete requirements. So the Rubin science is very broad, but we had to adopt a set of concrete things that we could flow down the requirements to specify exactly what was important on the observatory. And so we chose 4 main themes. One was probing dark energy and dark matter, or fundamental cosmology. The second was taking an inventory of moving objects in the solar system, so characterizing everything that moves in the sky. The third was exploring the transient optical sky, everything that varies. And the fourth theme was mapping the Milky Way. And I'll talk briefly about each of those. So let me first talk about dark matter and dark energy. So as its name implies, dark matter is dark. It doesn't emit any light. So how do you study it with a telescope? Well, the reason that this is due to Vera Rubin, but the way that we first knew of its existence is we would see self-gravitating systems for which there wasn't enough mass in the stuff that emitted light to have that much gravity. So that's where the conclusion came. There must be something else there which we're not seeing, dark matter that has mass and is responsible for gravitational fields, but doesn't emit light. But it turns out that dark matter is visible. It's visible in a particular way due to a phenomenon called gravitational lensing, which was first figured out by Albert Einstein when he developed his theory of general relativity to explain gravity, our modern theory of gravity. And in Einstein's theory, light is itself affected by a gravitational field. So if you have a light ray passing by a mass concentration, just like material particles will be, that light ray is bent by the gravitational field. And Einstein predicted this, and then it was later verified by Eddington and some other people. That sort of was some of the crowning evidence for general relativity being the correct theory of gravity. Now, how do you see dark matter? Well, what we believe is in the universe there are concentrations of dark matter. And so light from background galaxies has to go by those concentrations on the way to us. And that phenomena of lensing, the bending of light, is just like lensing due to glass lenses. Okay, it distorts the background. So the way we see this is very similar. If you held a glass lens up against a wallpapered wall, the glass is transparent, so to first order you're not seeing the glass, but you can easily tell it's there because when you hold it up to the wallpaper, you see the wallpaper is distorted. Now, looking out at the distant universe, the wallpaper are all the background galaxies. And so if you have a concentration of mass in front of the background galaxies, you'll see those images distorted. This is a simulation, and it's sort of an extreme case, which would apply to a massive cluster of galaxies. You actually do see, and there are now many examples of this, arcs on the sky, which are the distorted images of background galaxies passing through a gravitational lens. So there's no question you're seeing something there. And from that image, you can deduce how much mass is in front of those background galaxies, and most of that mass is due to dark matter. So you can measure it. You can actually map dark matter using this technique. That's an extremely important effect for cosmology. We can do it in strong cases like this, but we can also do it in weak cases, and we can make a map of the dark matter distribution actually as a function of redshift or distance out in the universe. So we can measure how the dark matter has clumped with time. The other major effect that we want to study is dark energy. The term dark energy refers to an even more mysterious phenomenon, the fact that the expansion of the universe is accelerating. This was discovered in 1998 by two independent groups, and it was responsible for the Nobel Prize in Physics in 2011. So you probably are aware that the universe is expanding. That's been known for many years. But until this discovery, we thought the universe was expanding but slowing down. Why should it be slowing down? Because everything in the universe is gravitationally attracting everything else in the universe. So if it started in some kind of explosion, the gravitational force should make it slow down as it continues to expand. So this was the expectation. And in the late 90s, people did rather precise measurements to try to measure that effect. And in fact, they found it had the opposite sign. The universe was not slowing down, it was speeding up. Very counterintuitive. It's kind of an anti-gravity effect. But it turns out that is consistent with Einstein's theory of relativity. If the entire universe, the entire vacuum of the universe is filled with an energy field that has negative pressure. Einstein's theory found that pressure actually acts like mass. And if the pressure is negative, then you can get repulsion instead of attraction. Now, we don't know what dark energy is. Why is there this mysterious energy field filling all space? Why does it have negative pressure? So that's why we call it dark energy. Turns out it's 70% of the mass energy of the universe, so it's not only important, it's actually most of the universe. We have no idea what it is. We don't know what dark matter is either, We don't know whether these two things are related or unrelated. It turns out to be kind of unusual that we're seeing both effects in our current epoch, because if you look at how the universe should expand, there's a region of time when dark matter should have dominated, and a region of time dark energy should have dominated. To find both effects means that we live at this really strange time when when this transition is just happening. So these are major mysteries. These are probably the biggest questions right now in physics for the last 20 years since this was discovered. Lots of ideas have come and gone for this, but we still really don't know what it is. Now, how do you study those effects with a telescope like the Rubin Observatory? Well, the only way you can make progress on this is to do things more precisely. You have to take more precise measurements of the cosmic expansion history. And there are various ways of doing this. Again, we do it all with the same data. So the same data we're taking will support all of these methods. You can measure the brightness of what we call standard candles as a function of distance or redshift. And the standard candles, I won't go into the reason, but they're called type 1a supernovae. We believe we know how intrinsically bright they are. And if we measure how apparently bright they are, we can figure out how far away they are. So that's a standard candle, which you can chart the expansion history of the universe. You can also measure the angular size of what we call standard rulers as a function of distance or redshift. A standard ruler is something that you believe you know physically what the length scale is. And then if you can measure its angular size, you can figure out how far away it is. And I won't go into the reasons, but the physical rulers we're using are an effect called baryon acoustic oscillations, which is a distance scale in the universe that we believe we know very accurately. And then the most interesting way, in my view, is by measuring the growth of structure as a function of redshift or distance. So the universe started out extremely homogeneous and smooth. But as it expanded, gravitational concentration started to develop. So if there was a little bit of excess mass in one area, it attracted more mass, and that attracted even more mass. So the universe became clumpy. And it's good that it became clumpy, because that's where the first stars came from, and the first galaxies, and eventually planets, and eventually us. So if the universe were not gravitationally unstable, it would have just remained this extremely smooth thing, and nothing would have happened. That process of gravitational instability is basically simple Newtonian physics. So we can calculate it. We know how it should proceed as a function of time. But the interesting thing is the universe is expanding underneath it. So that's countering that gravitational attraction. If the universe is expanding faster, it's harder to get the attraction to occur. If it's expanding slower, you'll get more. So if you can measure how clumpy the universe is as a function of distance or cosmic time, then that gives you a precise constraint on how the universe is expanded. And the main technique we'll do with this is this gravitational lensing effect I was telling you about. By seeing the dark matter, we can measure the clumps. And we can measure the clumps as a function of how far away they are, and that will give us this time history. So the Rubin Observatory will enable each of these different methods from the same database. There are about 2,000 scientists now that are collaborating together to perform these analyses with the data. And now that we're producing the data, we'll see what the results are. Okay, let me turn to the solar system. So this is an interesting plot which came from the Sloan Digital Sky Survey. So what you're looking at on the vertical scale is the sign of the inclination of these are plots of asteroids, known asteroids. For each asteroid, it has an orbit, so that orbit is inclined a bit with respect to the ecliptic plane of the solar system. That's the vertical axis. And the horizontal axis is how far away what is the size of that orbit in astronomical units relative to the Earth and the Sun. And the colors that you see, so each dot in that diagram is an asteroid. The ones that are different colors are because they look a little different. Asteroids have different composition, and they have different elements to them, and so they reflect light differently. So the different colors represent different kinds of asteroids. Now, for every one of the asteroids, you not only know where it is, you know its orbit. quantitatively its orbit. And so if you know the orbit, you can project it forward in time, or you can project it back in time. And even from these data, if you take all the green points and you project them back in time, you find out, magically, that they all coalesce at some point in the distant past. So all those green points were actually the same object. And the same for all the blue points and the purple points. Now, why are they now a lot of objects? Because these things banged into each other. They collided, and they made a bunch of smaller debris, and each of the piece of debris went into its own orbit around the sun in the solar system. So we made a bunch of pieces in the orbit. So by studying this effect, and with Rubin, we'll get millions of asteroids. So we can do this much deeper than Sloan did. You can trace out the collision history of the solar system. Actually, with time. You know in time when these things coalesced. You can figure out which things banged into which, and how that happened, and how that evolved as the solar system formed from its early stages. So it's a time machine. It tells us a tremendous amount of information about solar system history. So the other interesting thing about asteroids is that some of them could run into the Earth. And this has been a concern for a long time. You know, are there killer asteroids out there that are going to smash into the Earth and kill all of civilization? We sort of believe that the dinosaurs disappeared because of an asteroid event in ancient history. So this is a plot of what we know about asteroids. So on the vertical scale it's a log scale, as you can see, are the number of asteroids that are brighter than a certain brightness. Or you can turn that into how large in size they are. Or the number is the vertical axis, and the horizontal axis is how bright they are or how big they are. And you can see the data kind of look like a power law, which means on a log-log plot, it looks like a straight line. So on the right-hand side, you can see there aren't really many really big asteroids. But as you go to much smaller asteroids, then they get pretty common. So the number of such things goes up by a factor of 100 million or so. The red line, this plot is a few years old, but it hasn't changed much. The red line is an indication of what we actually know. I mean, which asteroids we've detected and we know. And so you can see that the really big ones, they're not that common, and actually we sort of know where they are. Now those are terrible. As I said, the horizontal scale is size, if you like. At the top is what we call impact energy, which is if something of that size hit the Earth, what size bomb would it be equivalent to in units of megatons of TNT? So you can see the really big asteroids would be a 100 million megaton bomb. That pretty much destroys the Earth. So it'd be really bad if that hit. But there aren't very many of them. And in fact, we know where they are. And none of them are going to hit, to our knowledge, in the near future. And at the small end, where there are 100 million or more of these smaller asteroids, they're equivalent to, a kiloton bomb. But they don't actually get through the atmosphere. Those smaller objects, when they impact with the Earth, they burn out in the atmosphere. So you don't really worry about those. But there's a sweet spot right in the middle. It's right about 1 kilometer in size, where there are a lot of these things, and we don't know them. We don't know where they are. We don't know how to predict it. So those are the ones to worry about, these 1 kilometer asteroids. And if you think about what would happen if one of those hits, well, the science fiction movies show the asteroid impinging on Manhattan. That's extremely unlikely because Manhattan is a very tiny fraction of the Earth's surface. So what's most likely is an object like this would fall in the ocean. But a 1 kilometer asteroid coming from space falling in the ocean would create tsunamis all over the world. So it's still a major issue for us, mostly for coastal cities, but most people live in coastal cities. So that's what the challenge is. And in fact, in the late 90s, there was a mandate given to NASA by Congress to find all the asteroids down to 100 meters in size, well enough so we would know whether any of them would hit. It wasn't clear what we would do about it if we knew. There were some fanciful ideas about what we would do about it, but that was the challenge. NASA never did this because it was an unfunded mandate and they didn't really know how to do it. But it turns out that the Rubin Observatory will find all these asteroids, okay? The colored lines here involve certain different assumptions. So as a function of how far away the asteroid is and how big it is, this gives our sensitivity to find them. And the mandate set by Congress is the blue PHA gold line. We get below it, which means we can easily detect everything they want us to detect that has any chance of getting to the Earth. Now, we pointed this out. So the mandate that went to NASA said, find all these asteroids by 2020. And we testified before Congress when we were trying to get this project funded about what we would do. And the question from Congress said, you know, are you going to find them by 2020? And we said no, because, you know, it hasn't been funded completely, and we're not going to have it built until 2025 or 26 or so. So the question from the congressman is, well, what are we supposed to do for those 5 or 6 years? That shows the sophistication of certain members of Congress. But the good news is that now that we're online, we will start finding these asteroids, and we'll address a lot of these questions. Okay, exploring the variable sky. We know of lots of variable stars in the sky, so this is a plot. The vertical axis is, you know, how big are the variations in a fraction of the light. The horizontal axis is, you know, what is the characteristic time scale of those variations. And the different colored points on this plot are just different kinds of variable stars. They have different names. I won't go into what they are, but we know about a lot of variable stars. So there's some progress in astronomy. This is not a new topic. On the other hand, we'll increase the number of points here by factors, in this case, probably 1,000. So we'll not only flesh out all of these known classes, but we'll discover new classes. The somewhat more interesting plot is these transient events, these things that are not periodic, but they suddenly flash. And on this plot, again, the horizontal axis is what is the characteristic time scale, and the vertical axis is how bright do these things get. You can see a lot of different categories of objects there, various kinds of supernovae, classical novae, other kinds of explosive events. There's a lot of known things. Now, if you notice in the lower left, that's where we put all the captions. Why do we put the captions there? Because there are no events there. Not because there are really no events there, it's just that we don't know because we've never looked. So these are very short duration events that are not apparently very bright, which means they're probably very distant cosmological events. So we don't know. So there's all sorts of new discovery space in this area that we'll get with this observatory, and who knows what we'll find. Maybe we won't find anything new. I think that's pretty unlikely. I think we'll find tons of stuff that's new, and we'll have to figure out what it all means. Okay, let me turn to the last topic, which is the Milky Way. This little inset that you can see in the beginning, in the middle of this plot, that's what's known about the structure of the Milky Way today. The biggest problem with studying the Milky Way is we don't know how far away stars are. We can measure how bright they are, we can measure where they are, but we don't know how far away they are. If you don't know how far away they are, you can't trace out the three-dimensional structure of the Milky Way. To date, we haven't been able to do that very much because we haven't had powerful enough telescopes. With Rubin, the blue thing is a simulation of what we'll learn. So basically, we will map out the Milky Way to its furthest extremities in a way that's never been done before. And one of the things that you can do when you do that is you map out what are called tidal streams. So if you look at the faint stars in the sky, you just see a field of stars. But if you can figure out which ones are furthest away and which ones are closer, then you actually start to see structure. And you see that in the distant regions of the Milky Way, stars are not randomly distributed. They appear in these streams, streaks. What are those streams? Those streams are satellite galaxies, smaller concentrations, galaxies, that over cosmic time have fallen into the Milky Way. And as a smaller galaxy falls into the Milky Way, tidal forces strip the stars out of it and leave a stream. So if you can measure these distances, and you can do this, we know of a few, that's what's shown here. We will discover hundreds and hundreds of these with Rubin. That shows you the full history of how the Milky Way was assembled. All of these smaller systems that over time fell into the Milky Way, leaving these trails of stars. So it's a really rich, again, Rubin provides a time history of the phenomenon that we're studying. Okay, so that's a little bit of the science. Let me just quickly go through some of the characteristics of how we built this thing. As I mentioned, we're surveying the southern sky every 3 nights for 10 years. We cover the whole southern sky. We do this with a 9.6 square degree field of view. The total angular size of the survey field is 18,000 square degrees, which is half the sky. And we need to do this to a very faint limit to get to the science we want to do. And we do that in 6 different color bands, which are done by using optical filters. It's a very big data set. I mentioned this, 20 terabytes, 20 billion galaxies, et cetera. And these are the 4 research areas that I talked about. This is mostly repetitive. At the right, you can see our simulations of how evenly we'll cover the southern sky. So the color scale is sort of how many observations do you get of each part. There are some variations. The black streaked region is the Milky Way itself, which eventually the star density gets so high we can't look there. But you can see it's a very even coverage. So let me talk a little bit about the project. The project is very complex. It has 3 main pieces to it: an 8.4 meter telescope, which is shown on the left, a 3.2 billion pixel camera, and a petascale data management system that can acquire all of these images, process them quickly, turn them into catalogs and products that we can distribute to the community. One of the big driving things for the Rubin design was that within 60 seconds of closing the shutter in Chile and a given image, we want to get all those data to the United States, process that image, find everything that's varied in that image against a template, and broadcast all those variable objects out to the world, all within 60 seconds of closing the shutter. Why is that the requirement? Because something fast has happened. You want to get other telescopes on it as fast as you can. And you're not going to get those other telescopes on unless you can alert and notify people really fast. So this is an alert system. The problem is we'll issue about 10 million alerts per night. So you're not going to take this on your cell phone. There has to be an intermediate sort of broker that sort of characterizes what these things are like, identifies which ones are the most interesting to follow up, et cetera. And so there's a whole industry now of work going into doing that. There are various kinds of data products. Let me not go into the details of this, but there were a lot of requirements on the data management system. We spent more money on data management on this project than had ever been spent on any scientific project. Usually data management is the poor cousin. You spend all the money on the hardware, you run out of money, and software will come later. But we knew that this was not going to work. We had to develop the software up front. And so we spent about $150 million on software, just software alone for all this. I mentioned the education and public outreach was a key element. of this program, and we funded it as a key development element. There are various parts to it. There's formal education, so there are products that will deliver to schools, colleges, et cetera. We have an active citizen science program, so ways in which amateurs and the general public can participate in scientific discovery by working with scientists to perform particular kinds of analyses. There are general public availability that anybody can log on, collect some data, do whatever they want with it by themselves. And then, of course, if we're producing tools for planetariums and science centers so that we get the word out there to as many people as possible. Let me say a little bit about the hardware. I mentioned earlier that the Rubin Observatory primary mirror is an annulus. You can actually see in this picture the mirror when it was being fabricated. You can see the change in figure in that glass. This is the first time a compound object has ever been made in a mirror like this. So the outer part of it is the primary mirror, and the inner part is actually the tertiary mirror. It's a 3-mirror system. The light comes in, bounces off the primary, then to a secondary, then to the tertiary, and then on into the camera. In order to get this to work, the tertiary surface and the primary surface have to be coaxial to within less than a millimeter over an 8.4 meter optic. That's extremely difficult. It's easy to make precise surfaces. It's hard to get them registered exactly where you want it to be. So there was this was a risky part of the project. We did it early to verify it. Never been done before, but remarkably successful. Now the mirror is actually a complex assembly. It's not just a piece of glass. It's an actuated piece of glass. Behind both the primary, tertiary, and the secondary mirror, there are something like 150 actuators that can push on that glass subtly to adjust its figure. We do that because as you tilt the telescope up and down, gravity tends to distort these surfaces. So you have to correct for it. So we need to measure this effect and actively control the optical surfaces as we're operating the telescope. That has been done before, but not in this level of detail. It turns out to be a very complex problem. I have a grad student who just graduated, got his PhD at Stanford, working with me on developing that whole active correction system. How did we do that? And then we need this stiff structure. So what we're really controlling with the telescope mount are these 3 reflecting surfaces and the camera. And so you have to embed those in some very large structure that you can move around the sky quickly and maintain that rigidity. And this was a major activity. It's a 300-ton moving structure, and it has to be precise. And it moves really fast, much faster than all telescopes that are its size, that are of comparable size. And this is the finished telescope in the dome in Chile, taken from a camera mounted on the dome. The observatory structure itself is kind of interesting. So you can see a picture of it in the upper right. It looks kind of like a steamliner, a yacht, some kind of large yacht. That's not unusual, time-wise. Okay. I'll finish up quickly. The reason for that is you put a telescope on the edge of a cliff, you want the air to come, and the first thing it hits is the telescope, because once it hits something, it gets turbulent, and that screws up the images. So you want it to flow over the telescope to give you clean air. So we did a lot of 3-dimensional modeling of the airflows in this vicinity to describe, to define what the architecture of the telescope assembly look like. The camera, as I mentioned, is 3.5 billion pixels. It's an extremely complex beast. It's the largest camera ever built. These are all the different components shown in an exploded view. I won't go through all the details here. This is what the final finished camera looked like, still at SLAC. We put it all together, and then we shipped it down to Chile in a dedicated airplane. This is what the focal plane looks like. It's 63 centimeters in size. It consists of 189 separate sensors that are close packed together, all with their own electronics, so we can read this out very fast in parallel. And this is the camera mounted on the telescope, which was just done last March. Let me just skip this. This is an interesting picture we took with the real camera of a photograph of Vera Rubin through a pinhole. And it's actually imaged on the camera array. The software system, one big element of it was to make a fully open system. So the idea is everything we produce is just made available to anybody who wants to look at it. This enables a lot of creativity in the community and allows people to repeat different analyses with ease. It's a very large group of participants that worked on this system. So these are all the countries in the world where scientists were involved. A lot in Europe, also China, India, Australia, even parts of Africa, as you can see, and of course South America. This was first light, April 15th of this year. Unfortunately, I couldn't be there because I'd taken this new job as dean, and Berkeley said, no, don't go down to Chile right now. We need you doing things. But this is the team of people I've worked with for 20 years. And these are the first images coming up, and you can see the expression on everybody's face. And this is one of a number of first light images. So this is a real image taken with Rubin. There are others available on the web. If you want to log on to the Rubin Observatory site, you can download them. I like this image. This image is of the Virgo cluster. Astronomers may recognize it. You can see the concentration of galaxies near the center of the field. That, of course, has been known for a long time. The really interesting thing you can see, though, is this sort of faint, low surface brightness stuff. So look at that pair of interacting galaxies in the upper right. Isn't that fantastic? Those are all the stars that are being stripped apart as two galaxies merge. And you can see the rich spiral structure of some of the other bright galaxies. So that kind of ability to get that faint light level combined with, such a large field, that's totally new in astronomy. So this is my last slide, just a timeline of where we've been on this. A lot happened in the last 2 years. In the fall, about a year ago, we shipped the camera from SLAC to Chile in a dedicated airplane. It was, we all had our fingers crossed. It's a really delicate instrument. The primary tertiary mirror was coated and installed. The secondary mirror was installed. We had a commissioning camera we put on the telescope before the main camera. And then finally, we installed the main camera on the telescope mount. Earlier this year, we took system first light. We had a media splash. I showed you one of the images. And right about now, actually in the next month, we're doing the official completion of construction and the beginning of 10 years of operations. So this is a really timely end. So let me stop there and thank you for your attention. Yes, first question.
Software engineer here, and 200 peta, that's about 10 good-sized rooms, and it's all at SLAC, and the San Andreas fault here and all that, so you have to have it distributed elsewhere, right, so that you don't lose it.
Yeah, we also have a data facility on site in Chile. I should say you might wonder how we get the data from Chile here. We actually have 2 redundant optical fiber paths, so we never lose data in transit. We will have an extra copy in Chile, of course. It'll be on disk. But, SLAC's lived on the San Andreas fault for a long time. so a lot went into the construction of that building, and we believe, barring magnitude 8 earthquake or something, it'll probably be okay. Thanks. Yeah?
Why only 10 years?
That's a very good question, and it's kind of a round number. It's a human timescale. You know, it's not going to be 1 year. It's not going to be 100 years. So 10 years is what it is.
Well,
now, people often ask, well, why would you stop? Why wouldn't you run it for 20 years? And the truth is, most of the science, not all, most of the science with Rubin scales like the square root of time. And so going from 10 years to 20 years is just the square root of 2. Now, there is science like very rare events, and it turns out the astrometry that scale either linear in time or faster than linear in time, and that science will get much better towards the end of the 10-year period. And we probably won't stop in 10 years, but when you build a project with federal money, you have to have a definite cost. So we had to say, we define the project to be 10 years, and this is what it will cost to operate it for 10 years. When we get to the end of 10 years, of course, people will say, well, let's keep operating it. It's been wonderful, and probably that will happen. But we had to baseline it that way. And then all the science, then we mapped all the science that we could do it in 10 years if it was shut off then. Yep.
Are you a believer? Do you believe in Planet 9? There was some talks here in this auditorium about Planet 9. So do you think there will be a chance to observe it within the next 10 years?
Yeah, I think we will certainly find it if it exists. We have the capability, and with this frequent observation, we will find it if it exists. And so, you know, whether the evidence to date is sufficient or not, I don't really have an opinion on. But there will be people looking for objects in that class, certainly with the data. And we will find them if they exist. Yeah.
Thank you for the amazing talk. And I have so many questions, but I will limit to just one and ask, what frequencies of light does the Rubin detect? And also, what is the quantization? Like, is it taking red, green, blue pixels, or is it something?
Yeah, so it's a visible light telescope. It goes over the full visible range from the near UV to the near infrared. So in technical terms, it goes from about 300 nanometers out to 1 micron. And that's covered in 6 different filter mounts. And it's essentially a photon counting instrument. Every photon will, with essentially unit probability, produce an electron. And so when we read out the charge in the CCDs after each time, we will measure linearly the number of photons in that sense. Yeah.
Hi, just a quick question. Why is the Vera Rubin program only running for 10 years? Is it because of like a quality issue or funding?
Yeah, that was just asked before. It was so, we had to pick a duration. And so 10 years is a round number. So it's not going to be 1 year, because you wouldn't spend $1 billion and only run it for 1 year. It's not going to be 100 years. So you have to choose a duration, spec the hardware to last that duration. So everything is, that's part of the requirements, that we look at the failure modes, you know, that it won't fail in 10 years. And then we cost out how much it costs to operate it for 10 years. Now, as I said, you know, when we get to the end of 10 years, there may be enough interest to keep running it. There may be some interest in modifying it and continuing to operate with a different science program. We'll see. But for this project, we had to define something, and that's what we defined. Yeah.
Hi. First of all, thank you so much for your time and giving us this talk. I have a bunch of questions, but is it okay if I ask 2 quick ones? Okay. I guess I would ask, where would you encourage people to start out getting involved in citizen science on Rubin's website?
You can find it on the web. Okay, so go to the rubinobservatory.org.
What particularly do you feel most excited about in terms of citizen
So historically, there's been a lot of citizen science and galaxy classification. There's now some of the more interesting programs, newer programs, have been in characterizing strong lensing systems, which have a time profile to them. So there's work to do there. I will say it's a bit of a challenge because of AI. AI has improved such a way that a lot of things that we used to think you need citizen science to do, AI can sort of do. And so, you know, that gets a little more specialized in what is a unique thing. We'll still run the citizen science programs because they're fun and people like to get involved with them. But a lot of the things we thought it was critical to have a bunch of human eyes working on, we'll probably do with machine learning and AI techniques at this stage. So we won't be totally dependent on it. But that doesn't stop people from getting involved. Yeah.
Thank you, and congratulations.
Thanks.
I just want to echo Andrew's reaction and say, wow. Incredible bang for your buck, if I can editorialize, when you compare it to you know, multi-billion dollar a year project like Artemis. My question, I'll limit myself to one because I have many, very specific. Do you think you'll find an object that New Horizons can visit in the future?
Yeah, it's an interesting question. So I mean, we're not exactly ideally suited to exoplanet detection and sort of things in that kind of category, but we'll definitely discover a lot of phenomenology that may be relevant. So yeah, so I think the answer is probably, but I couldn't tell you exactly what that's going to be right now.
Well, my fingers are crossed.
Yeah.
Does the telescope have spectroscopy capabilities?
No. So we chose deliberately not to do that. And the reason is, you know, the idea was a uniform survey that covers as frequently as possible the sky. We thought at some point early on, maybe carving out part of the focal plane and allowing light to come through to a spectrograph. But it would have, you know, it wouldn't have really been a survey because it would have been only a small part of the field of view, so we wouldn't have gotten very many spectroscopic objects. Rubin is not great to be a follow-up telescope. It's a discovery telescope. Once you know where something is, there are other telescopes that you can use to do spectroscopy and point at. So the only category of sources right now we're thinking of doing deliberate pointing with Rubin at are gravitational wave events. And the reason is those are not so well localized. So the very large field of view with Rubin is great for finding where the actual event is from. But we don't do spectroscopy on this. On the other hand, we have lots of coordinated programs with other telescopes with spectroscopes in various different wavelength bands that can immediately go to a source once we tell them where to look and when to look.
Is capability to mapping out all asteroids, would you claim?
We have a lot of people waiting, so one per person.
All right, sorry.
So we have 3 more questions.
Okay, great.
Hi, my name is Raymond. I had the pleasure and experience of working on the Stanford Elliptic Accelerator over the last several decades as an electrician, energizing it. So the Rubin is in a quite remote area in Chile.
Right.
And I was wondering what energizes the complex and how reliable is that source?
Yeah, right. So we have power lines running up the mountain, and they were actually there before we built it for the other telescopes that are in the vicinity. We also obviously have backup generators because those lines go out, but we strengthened the whole electrical grid system up there for Rubin, and we had to lay brand new optical fiber to get from the mountain down to the coast.
What is the length of that?
100 kilometers.
Pardon me?
100 kilometers.
And
so we spent 10 million.
How reliable is the source?
It's, you know, we have had power outages already since we've been on it. It's not uncommon. As I said, we have backup generation. It hasn't been too bad a problem right now.
Thank you so much.
Yeah.
Yeah, hi there. I'm a software engineer by profession, but I studied physics a long time ago. I was just curious whether you think whether Rubin will be able to help arbitrate the Hubble constant tension.
Yes, right. So some of you may know there is a tension in the Hubble constant. It has to do with measurement. The Hubble constant is how fast is the universe expanding today. And the measurements of local objects give you a value, and then there's a value you get by looking at the microwave background, which is emitted at redshifts of 1,000, roughly. So near-term measurements versus distant measurements, they should agree if the cosmological model is correct. They don't agree. Right now, the discrepancy is about 5 sigma, but that discrepancy depends on what kind of stars you're using to measure the Hubble constant locally. So the supernova measurements give the 5 sigma discrepancy. There are other ways of using other stars, and they're closer to the microwave background thing. So there's still a lot of room there. There are other tensions with the current cosmological model that, if they're real, Rubin will find them at 15 sigma or so. So we will establish with full confidence whether these cracks in the cosmological model are real or not. I'm very confident about that. Whether we'll figure out what they mean is another story, but we'll certainly improve the measurement by a huge factor. Yeah.
Okay, thank you. Yeah, I guess we'll probably find new questions too that
for
you
sure.
don't even think of today.
Yeah,
Thanks.
for sure.
We have to stop there, but let's thank Professor Kahn.